Welcome back. In the last class, we started discussing about several practical aspects concerning recording of the NMR spectrum. And afterwards, we have to discuss about how we have to process this data. Of course, in the last class, I gave a lot of information about sample preparation, the type of NMR tube you have to use. You have to choose appropriate solvent. Locking out the signal deuterated solvent is very important to see that to avoid the drifting of the magnetic field. And I also said how to choose the spectral width. Of course, I said we need to acquire the data so that we should not truncate the FID. At the same time, we need to acquire sufficient enough to see the signal. And I also mentioned if you acquire signal for a longer duration, more than what is required, that is after the signal dies down, you will be acquiring more noise than the signal. As a consequence, your signal to noise ratio will come down. That is also not advantageous. So there are many parameters which you need to optimize before recording the spectrum. So today we will continue further and let us see how we have to choose the spectral width. I said we should have a spectral width that also defines your resolution and how much time the signal is taking, how long you have to acquire, everything we have to decide. For example, acquisition the time required to acquire the time domain signal. You send a radio frequency pulse, start collecting the signal. How long you acquire the signal? That's what I said, you have to acquire signal and you have to optimize it. How do you optimize it? That depends upon number of data points, that is number of data points, and that is divided by twice the spectral width. It's a very important parameter. The acquisition time, this one defines the digital resolution. See, you can't have a shorter spectral width. If you have a shorter spectral width, your acquisition time becomes longer. You have to acquire a signal for a long duration. Probably your signal would have died down within few seconds, but you may still be acquiring signal for few more seconds. That's not good. If you take large spectral width, your acquisition time is very short. Then you may truncate the FID. You will not be collecting the FID for longer time what is required. So you have to decide on this parameter. You have to optimize it. And the acquisition time is what is that which decides, the one which decides digital resolution. That is called hertz per point. See, NMR data, when it is collected in the time domain, it is digitized. After Fourier transformation, you will see the frequency domain is also digitized. When you are digitizing the time domain data, how many times you have to digitize? And let us say I start digitizing here there is a free induction decay. Let me tell you here, I have a peak here. I have to start collecting the signal at different points like this. I will digitize and I collect. And the time between this and this are between any two data points, the hertz between these two data points, let us say, is what is called digital resolution. The digital resolution is defined by these two data points. Let us say I collect one data point here, another data point here, then you will not be able to resolve the spectrum at all. There is no digital resolution for it. On the other hand, let us say this peak has two peaks. Actually, it is a peak like this. That is a doublet. But you collect one data point here, one data point, and one data point here. Then you will miss the doublet because you are not getting good resolution. So, the number of data points you acquire and the duration for which you are going to collect the signal defines your digital resolution. It is called hertz per point. And the time between two data points is called dwell time. That is a very important. This defines the dwell time. The shorter the dwell time, better is the resolution. Remember, shorter the dwell time, better is the resolution. So, how you decide the number of data points? Say, manipulate this equation. If it is the number of data points, you have to decide how much you have to give. This is acquisition multiplied by twice the spectral width. I said acquisition time and digital resolution are inversely proportional to each other. And this is the equation. This tells you how many number of data points you need to collect to get good resolution. Okay, you can decide that. For example, I have a 500 megahertz instrument for which I have to acquire data for 10 ppm. You all know 10 ppm in 500 megahertz correspond to 5000 hertz. Let us say I have two peaks separated by 0.5 hertz. I want to get a resolution of less than 0.5 hertz so that I can resolve two peaks like this which are separated by 0.5 hertz, let us say. So if that is the case, how many number of data points you have to choose? That you can decide based on this equation. Twice the spectral width divided by digital resolution. And this will tell me about my resolution. So my digital resolution should be at least 0.25 hertz. So dwell time between two data points, it should be 0.25 hertz. Now for 10 ppm, I have to take 5000 hertz. This is twice the spectral width, so it is 10,000 hertz. Divided by 0.25 is the digital resolution I expect or I want. So the number of data points I must choose should be minimum of 40,000 points. Okay, the what you call as data point CD or SI, the size of the memory, what you are going to collect should be at least 40,000 points. Okay, and if you cannot take the odd number like this, especially for acquiring data, this is called in your spectrometry, it is called SI. Okay, so but time number data point is different. This is the data point for which you are going to. I mean, it is let us say size of the memory. Okay, SI. So these data points has to be in multiples of 2 to the power of n. And so you cannot take 40,000. Of course, time domain points you can choose any number. That's not a problem. We have provision for it. But at the time of acquiring, if I want to have this, yes, the memory of the computer for which you are going to collect the data, it has to be in the multiples of 2 to the power of n. It should be 32K or 64K, like that, or 16K. You have to choose based on number of points you have to choose. Supposing instead of for 0.25, I need minimum 40K data points. Let us say I take only 10K data points or 10K points. Okay. If I collect a signal and I will use size of the memory, okay, size is only 10K I'll take. Then you will not get that much resolution. So you'll be missing 2 points or 2 peaks which are close in space. Please understand. Okay. So digital resolution, if it is 0.25 in a 500 megahertz spectrometer, minimum I have to acquire, I should have size of the memory should be at least 40K. Okay. Now what happens? Based on that, I can, of course, after acquiring data, you can play with the time domain data also. There also increase number of data points. It is as good as telling indirectly, you are increasing the size of the memory, size of the data points. Okay. Memory size. See now, consider this is an example of a spectrum where you have 2 peaks which are resolved, no problem. But look at this, the number of data points here. As a consequence, you are not getting good spectrum. Supposing if this data point is missing, you would have got a peak like this. Then you will not get resolution and you will not observe this as 2 peaks. You get the point. This is a situation as a hertz per point or dwell time is quite large. The resolution is poor. On the other hand, now the instead of 3 hertz, I'll take the digital resolution to be 0.3 hertz. That is data between these 2 points. Any 2 points you take adjacent points, this this is called a dwell time, and I this should be 0.3 hertz. Let us say I take digital resolution. The resolution between any two data adjacent data points is 0.3 hertz. Look at the type of spectrum you are going to get. It is better resolved. You can see the resolution. You cannot miss this doublet at all. But in this case, if you make a mistake or slightly more than 3 hertz are there, you will definitely not be able to see doublet. That's important point you must remember. Digital resolution is very important in getting better resolution. You see the effect of digital resolution on some standard example like this. This is a situation, number of digitization points is n. Let us say number of digitization points is n. And spectral width is some value, it is taken. When the hertz per point, dwell time is 6.6 hertz. Look at the spectrum, so broad. The same thing, reduce the hertz per point to 3.3. See, you already started seeing the resolution. Keep on reducing like this. Come to 0.105 hertz per point by playing with number of digitization points or the spectral width. Reduce the spectral width or increase the number of the digitization point, number of size of the memory, size of the digitization points. In which case, you see what you would have seen with a poor resolution as a broad hump, now you will see as doublet of doublets. You understand? The effect of digital resolution is so good and so important. So proper choosing of the spectral width and the number of digitization points is very important to achieve very good digital resolution to see well resolved spectrum. Okay. So now I would like to based in the when we are discussing about digital resolution and also number dwell time, I will introduce one more term called folding, or in Fourier transformation, it is also called aliasing. Folding or aliasing. As you know, FID is acquired in a digitized fashion, and this is the digital resolution. That's what we discussed just now. The spectral width is determined by the digital resolution. That's correct. That's what we said. Now, the question is to characterize a frequency correctly. How many digital points are required? For example, in this case, look at this one. Now, not this one, you look at this one. Here, we have 1, 2, and 3 points to define a peak. Here, there are 3 points to define a peak. But still, you are able to identify 2 peaks here. Here, you have more number of digital points. That is better. Supposing, if I had missed this peak, what would have happened? You would not have seen the doublet. Correct. Now, another extension of this is, if you do not have enough number of digital points, you get into a problem called folding or aliasing. This is because of what is called Nyquist theorem in Fourier transformation. Let us say I have a spectrum with the different frequencies from 0 to 10 ppm. Let us say I have taken the spectral width 0 to 5000 hertz. Okay, 0 to 5000 hertz I have taken. There is a peak here. 0 to 5000, at 5000 I have a peak. This is my largest frequency. You see, this is my largest frequency. And if the highest frequency in the spectrum is F maximum, if I have to represent it correctly, and not only that, all the frequency lower than that will be represented correctly, then digitization should be such that F of maximum should be at least equal to 1 over 2 times the digital resolution, at least 1 over 2 times. If 2 is missing here, 1 or 2 times the digital resolution. If not, the frequency higher than f maximum, that is, if I have a frequency beyond 5000, let us say at 6000, 1000 hertz more than maximum, f plus delta appears as f minus delta. Remember, this is 1 hour twice the digital resolution. Remember, don't get confused in Nyquist theorem. The 2 was missing. At least you have to digitize twice. For highest frequency in the spectrum should be at least digitized twice so that frequency can be represented. If what happens if the frequency is, let us say like this, you digitize 1 point here and 1 point here, you will definitely miss it. So it cannot happen. Higher the number of digitization points, of course it should be minimum 2. You have to have 2 data points per peak. More than that doesn't matter. So this is what it is. According to this Nyquist theorem, it says it should be the highest frequency should be at least 1 hour 2 times the digital resolution. That is Nyquist theorem. Otherwise, folding will occur. For example, look at the spectrum. For example, look at the spectrum. This is a free induction decay. It is digitized. Of course, I am showing you only single frequency oscillation here. The damped oscillation is only for single frequency. If there are more frequencies, you would have got an interferogram. For representation purpose, I have taken only one frequency. Now, is it represented correctly here? Look at it. Number of data points 1, 2, 3, 4, 5, 6. It is definitely, it is digitized precisely because this is the, you can measure the frequency from this, right? From this oscillation. I know the frequency. So in this, from here to here is lambda, you know the frequency that shows 1, 2, 3, 4, 5, 6 points. Minimum 6 to 7 points are there. It is digitized much better, more than what is required. You require at least twice digitization. This is digitized much more than that. So this is very well characterized, very well represented correctly. On the other hand, look at the free induction decay at the bottom here. There is 1 point here and 1 point here and 1 point. So this frequency is not well characterized. At least there must be 2 points for each frequency, but it is not there. So it is not digitized at least twice and does not obey Nyquist rule. The Nyquist theorem says that sample should be free induction decay should be sampled at least twice of that of the highest frequency available. So F maximum is equal to 1 or 2 times the digital resolution. That is the condition you have to maintain. Otherwise, you get a spectrum like this. Let us say this is the correct spectrum. But if the digital resolution is here, like I say, I am sitting here. This is a carrier offset. I will tell you how to set it. And if there is a peak somewhere here, okay, then it appears as if the peak which is here gets folded here. Let us say sitting from here, I cover this much range. I have a frequency here, some lot of peaks here. This peak is not very well represented because my digital resolution is taken for only highest frequency within this region. So the peaks which are coming with a higher frequency than this chosen range will get folded here. This is called folding or aliasing. You understand? So that's what happens. Now, well, I said sitting here and I'm covering here, this is folded here, or sitting here covering this much, this gets folded here. Either way is correct. Okay. So now the question is, I collect one time domain signal, FID. Signal is very poor, let us say. Intensity is not very good. I have to enhance the signal intensity. Can I do that? Can I keep on adding the signal once, twice, thrice like that? Keep on adding. Is it possible to do? Yes. You can do that. NMR signal can be co-added in time domain. In the time domain, you send the radio frequency pulse, collect the free induction decay. Send another one, collect the free induction decay over this. You keep adding it. Then what happened? At the end, when you do the Fourier transformation, you will see the enhancement in the signal intensity. But you may also ask me a question. What happened? There will be also a thermal noise. Noise will be invariably present. Generally, we will have white noise. White noise is the one which has all the frequencies. So, what to do? So, noise has all the frequencies present and has random phase, whereas the peaks are always in phase. They get added up. Co-addition of this is easy, whereas noise cannot be added up in phase. They are random in phase. As a consequence, this also get added up, but not linearly. Free induction decay, the peaks from the sample which are in phase, they get added up linearly, but noise will not get added up linearly. So as a consequence, after you keep on acquiring for a long duration, because it's a random phase, when you take the average, this noise keeps on reducing. Whereas what happened to the signal? You are co-adding it in phase. They keep on adding up. Then signal to noise ratio becomes better. This process of co-addition of free induction decay in the time domain is called signal averaging. Remember, it is called signal averaging. The time domain signal is accumulated at regular intervals. Like this, you start collecting the signal here. There is a time which I will tell you what is this relaxation time, how much you have to give. Apply a radio frequency pulse. There is a time delay here, it's called dead time delay. Okay, and then start collecting the signal. This is one experiment. This is one time when you want to acquire a signal, this is what you do. Please understand. Send a radio frequency pulse and collect the free induction decay. That's all. If the signal intensity is very good, then you don't have to bother about co-addition. You don't have to bother about signal averaging. Fourier transformation of this one will give you frequency domain spectrum. But generally, it is true for a highly abundant spins like protons and fluorines. You may get the signal very fast. What happens if you take less abundant spins? For example, you want to see nitrogen in natural abundance. You cannot get the signal in one scan or one accumulation. Okay? So we are acquiring data once, we call it as scanning once. So it is one scan. So you keep on adding, you have to increase the number of scans. So what you will do, this is the first scan, and afterwards wait for some time and then send a second radio frequency pulse, acquire signal. Then after some time, send third radio frequency pulse, acquire the signal. So what you will be doing? Same one-dimensional experiment of sending the pulse and acquiring the data, you are repeating n number of times. And n number of times, you will be co-adding the data. This will give you enormous gain in the signal intensity. Enormous means how much? If I acquire once and twice, is it enough? If I acquire twice, then how much gain I will get? If I acquire 100 times, how much gain I get? These questions we have to answer. That depends upon a factor, a parameter called signal to noise. The signal to noise ratio is measured as S by N, height of the peak. Oh, I'll say I'm selecting a region for which I have to find signal to noise ratio. In that region, if there is a peak, I'll find out height of the peak and multiply by 2.5 divided by peak to peak noise height. You may ask me the question, why I have to multiply by 2.5? It comes by noise. If you want to understand how to get the signal to noise ratio, etc., you will get it. Don't worry, we will not go into that theory. But I am giving you the final solution. For S by N, you have to get the height of the peak, multiply by 2.5 and divide by peak to peak noise height. Peak to peak noise height you will get like this. This is the noise. Let us say you blow up the signal several times. Increase the vertical intensity. Now you get the maximum noise. Okay, in the representable form. Measure from this point to this point. What is the height of the peak? That is peak to peak noise height. Put that in the denominator. If I have a peak here like this and measure this height, this is the height of the peak. You understand? And then you calculate signal to noise ratio. Now the question is, if you want to do a proper experiment, you need to repeat the experiment with appropriate delay. In the previous example here, I gave you relaxation time here. What is this relaxation time? If I have to repeat it n number of times like this, let us say I send the pulse here, immediately I send another pulse here, immediately I send another pulse here, without waiting for relaxing this, for the nuclear spins to relax. Then what will happen? You must understand what is happening. We also discussed a stretch after the free induction decay starts decaying. This is called time domain decay in the transverse plane. It is called T2. It depends upon the relaxation time T2. Okay, it has to decay. If it decays completely, at the same time, the signal will be growing along z-axis. The decay in the XY plane, this is called a transverse magnetization. I remember we discussed this at one of the classes before. The decayed magnetization will grow along z-axis. It is an exponential growth. Decay is also exponential. But the time periods for decay and growth are different. Okay. Now, I must know how much time it takes for this spins, okay, for this magnetization to go back to z-axis and attain thermal equilibrium. The time it requires to attain thermal equilibrium is called spin lattice relaxation time. That is the one which defines what should be the relaxation time. Remember, the relaxation time should be such that FID has to go back to thermal equilibrium. In principle, you must wait for 5 times the longest T1. Why? Because remember, when I explained to you about decay of the magnetization and growth of the magnetization, I gave you an equation. The magnetization mz coming back to z-axis is equal to m naught into 1 minus e to the power of minus t1 by t2. T by t1, okay, take it. T by t1. That's what I said. So it is an exponential function. It means, remember, you put t is equal to t1, what happens? It turns out to be 0.67. If t is equal to 2t1, t1 is equal to, let's say, twice t, like that you calculate. T by t1 is there. Make it equal, then make it double, make it triple, find out. When the time delay t is equal to 5 times the t1, 1 minus e to the power of minus t by t1, that is the equation, right? 1 minus. If it has to get full 1, mz should be equal to m naught. That is a thermal magnetization, right? Equilibrium magnetization. If it has to become mz, has to become completely m naught, which was there before application of the pulse, then t should be equal to 5 times t1. You put the value into that equation. Mz equal to m naught into 1 minus e to the power of minus t by t1. Then you will find out this exponential factor turns out to be 99.999, whatever that number, second or third decimal you can take. That means mz is almost equal to m naught. The magnetization would have recovered 99.99% along z-axis. Then you have to apply another pulse to get the signal. You understand? Supposing you don't wait for that 5 tm, I would say I would send the radio frequency pulse. Signal will be there. I start collecting signal, and I don't wait for 5 times the t1. Then let's send another pulse immediately without waiting for even 1 t1. What will happen? Magnetization would not have grown along z-axis. As a consequence, what will happen? You will not get the signal. You will be only acquiring the noise. So waiting to send the second pulse for signal averaging is essential. That relaxation delay is essential, and it should be at least 5 times the longest T1 of your sample. If there are so many protons are there, each will have a different T1. You have to find out the longest T1, give 5 times that value, then you will get all peaks of nearly equal intensity and get maximum signal. Otherwise, you will be acquiring only noise. Now you may ask me a question: why should I wait for 5 times the T1? Supposing my T1 is several hours or not minutes, not second, minutes or hours. I am wasting my time. There are many methods to increase the relaxation, especially in the solution state, to bring down the relaxation by using certain methods, certain like some shift reagents, everything we can use, or chromium acetyl acetate. We can add a microgram quantity to bring down the relaxation. There are several methods. Also, you don't have to wait for 5T1. If you wait for 1T1, find out when T is equal to T1, 67% of the magnetization would have come back. 2 times you find out how much. 3 times T1 already 95 to 96 would have come back. That's enough. Only you are losing 3%, 5% intensity, 5% signal. Or if you apply only, wait for only 1 times T1, you will be losing 33% signal, right? So you can play with that. So you don't have to bring the magnetization to z-axis by 90-degree pulse always. You can use different angle and calculate how much is the magnetization you will get back and how much time you have to wait, and you can optimize the experiment. This is only the tip of the iceberg I am giving you. There are a number of ways you can. There are a number of improvements are there, modifications are there, where we know how much is the pulse width, what should be the time you have to wait to get a good signal to noise ratio, what we have to do, and many pioneers have contributed significantly, and you can follow that. But right now, I'm giving you the basic idea. If you want to do the signal averaging, you must acquire at least 5, wait for at least 5 times the T1. Now, if the number of accumulation is, let us say, for P, then signal to noise ratio we calculate is K. For doubling of that, what you have to do? You have to, let us say, I take 2 times the signal to noise ratio I want to get. The number of accumulations must be P squared. Remember, signal to noise ratio will go with the square root of the number of accumulations. Give you an idea. If signal to noise ratio is, let us say, 2, I want to make it 4. What you will do? If the signal to noise ratio 2, I could get in 4 scans. If I have to make this 4, I have to acquire 4 square number of scans. I have to acquire 16 scans so that the signal to noise ratio, it was 2, can become 4. Remember, the signal to noise ratio always goes by square root of this one, okay, number of accumulations. And this type of acquiring the signal one after the other for improving the signal to noise ratio is called signal averaging. Please remember signal averaging. So now what I am going to tell you is the time required for each scan is acquisition time plus the repetition time. Acquisition time is the time for which you acquire signal. So if you have dilute samples like less abundant spin like carbon-13, nitrogen, etc., you have to wait for longer time because such nuclei also have longer T1. Okay, and this is a picture which shows you if I have one free induction decay, you acquire one signal and do the Fourier transformation. This is signal to noise ratio. Co-add 1 plus 1, now it is 2, it is like this. Add 3 FIDs, signal to add 4 times, it should be exactly double, you see. That will become 10, signal to noise ratio was 10 here, it became 20, you see. In the signal to noise ratio, if you have to double it, the number of scans, number of accumulations should be square of that. Signal to noise ratio goes by square root of the number of accumulations. Okay, so I am going to stop it today here. We will come back and continue further tomorrow with some more information about data acquisition and processing.